a stellar explosion of such intense magnitude that it produces a massive burst of energy that is more than 10 times that of the lifetime output of our Sun. This explosive phenomenon is called a supernova. On the night of February 23, 1987, at the Los Campanas Observatory in southern Chile, Ian Shelton photographed the large Magellanic Cloud. As he developed his plates, he saw a bright object that was not on the previous plates. He thought it was only a flaw, but he walked outside to check it. In the sky, he saw a star he'd never seen before, an object appearing so suddenly he knew it must be a supernova. Ian Shelton telegraphed his discovery to the International Astrophysical Union. Using global computer networks, the IAU announced to the world the discovery of one of the biggest cataclysms that one can imagine in the universe. Designated SN 1987A, the supernova is located in the Tarantula Nebula in the Large Magellanic Cloud, the galaxy nearest to ours. Even though the supernova is 170,000 light-years away, it's the closest supernova since Johannes Kepler saw one in 1604 in the Milky Way. It's a rare experience for a supernova to be visible to the naked eye, although in 1054 the Crab supernova was visible even in daylight. For its part, supernova 1987A was clearly visible at night. It was once a faint star, although in fact a blue supergiant, about 15 times the mass of our Sun. But a star is always subject to its own gravity. When its hydrogen becomes depleted, gravity will take control and the core of the star will contract and get hotter. The supernova will occur at the end of a massive star's lifetime, when its nuclear fuel is exhausted and it is no longer supported by the release of nuclear energy. If the star's iron core is massive enough, then it will collapse. In this giant nucleus, the protons and electrons of the iron are so close to each other that they combine to form neutrons. Thus, the core of the collapsing star becomes a giant ball of neutrons, a neutron star. If a collapsing star were big enough, its gravitational force would overcome even the forces that hold atomic nuclei together, and the core would become a black hole. But if the star is not massive enough to form a black hole, it reaches a point where its core cannot collapse any further. At this so-called point of maximum scrunch, the core bounces back and blows the rest of the star out into space with an explosive energy more than 10 times the lifetime output of our Sun. This explosion is called a supernova. The energy emitted by a supernova is primarily composed of neutrinos, particles that very rarely interact with matter. Neutrinos can be detected in huge tanks of purified water buried in mines in Japan and the United States. 3 hours before the first optical observations of the supernova were made, these detectors noted neutrino emissions somewhere in the direction of the Large Magellanic Cloud. The neutrinos interacted with the purified water and caused flashes of light which registered on photodetectors in the tanks. These detections were not discovered until later, but they confirmed theories about how a supernova explodes. The energy of the star creates a super-strong shock wave that runs outward towards the star's surface. When the shock wave reaches the star's surface, it very quickly heats the surface layers and brightens them. This is the moment when distant observers first learn that a supernova is exploding. In the year following the supernova, several experiments measured extensive gamma-ray radiation. The data was gathered by NASA's Solar Maximum mission already in orbit around the Earth, and instrument-laden balloons which were launched in Australia. Japan launched the Genga satellite, which detected some of the scattered X-rays. NASA's rocket experiments launched from Australia also experienced radiation over several wavelengths. Other rocket-borne missions and the International Ultraviolet Explorer observed the ultraviolet spectrum. These measurements revealed information about the density and temperature of the supernova. and the formation of molecules surrounding the supernova and in nearby space. The Kuiper Airborne Observatory flew several experiments over New Zealand to observe in this region of the spectrum. Since infrared wavelengths are absorbed by the air, the experiments were conducted high in the atmosphere. Observations in all ranges of the spectrum were made. Scientists were able to gain valuable insight into natural lithosynthesis, the formation of heavy elements. Our solar system was created from these elements, and so the study of the deaths of stars will enable us to gain a better understanding of the history of our Earth and the rest of the universe.